we're going to be continuing through section 1.2 with scientific notation. So this is used a lot in fields such as chemistry, biology, and so forth. So our x is expressed through a number a times 10 to some power. So our a is between 1 and 10, not including 10, and our n is an integer. So for example, we have 6.4 times 10 to the 5th is 640,000. So this is our scientific to decimal way of doing things. So if n is positive, we're going to move the decimal point in a to the right n places. So since it's 5, we're going to go right 5. So it's 1, 2, 3, 4, 5. And that's why here it's 1, 2, 3, 4, 5. And then if n's negative, we're going to move it left to the absolute value of n places. So here it was like 2.17. So we're going to move it left 3 times. 1, 2, 3. And then when we're going from decimal to scientific notation, we're going to determine a and then move decimal point to obtain a number whose absolute value is between 1 and 10. And then we have to determine n, which is the exponent on n. So here it's a little bit different. N is going to be positive if the decimals move left, and then n is negative if the decimal moved right. So let me go ahead and go through an example to demonstrate this. So here, that's our decimal right here at the very end of this very large number. So we're going to move it up until we get a number who's between 1 and 10. So here, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I stopped there because 3.4, that's between 1 and 10. So I didn't stop behind the 7 because 3,497 isn't between 1 and 10. So since I moved the decimal left and 13 places, we have 10 to the 13 and then 3.497. So let's do some examples when we do some computations and scientific notation. Okay, so here's an example. So I have 6.1 times 10 to the 5th, 4 times 10 to the negative 9. Okay, so let's go ahead and regroup the terms in our expression. So I'm going to go ahead and group the numbers, and then I'm going to go ahead and group the 10 exponents. So I have 6.1 times 4 times 10 to the 5th times 10 to the negative 9. I'm going to change this so we're not confusing it. Okay. So here, so 6.1 times 4, we can use a calculator for that. So that's just 24.4 times, and then this, we're going to use our exponent rules. So 5, and then we're adding negative 9. That's going to get us 24.4, negative 4. Okay, so here 24.4 isn't between 1 and 10. So what I'm going to do is I'm going to look at that and just deal with the 24.4. Don't worry about the 10 to the negative 4 right now. So 24.4, that's equal to 2.44 times 10 to the first. Because if I move it up 1, that's going to give, I moved it one place, so it's going to be positive 1, and to the left. So I'm going to go ahead and rewrite this as 2.44 times 10 to the first, and then times 10 to the negative 4. Okay, so now I could group the 10 to the first and the 10 to the negative 4. So 10 to the first times 10 to the negative 4, we're combining those, oops, I accidentally put a negative. Sorry about that. So that's going to be 10, 1 plus negative 4. That's equal to 10, negative 3. So that's our answer, 2.44 times 10 to the negative 3. Okay, great job. Now I'm going to go ahead and end this video, and then I'm going to go ahead and start another video, continuing with section 1.2, and it's going to be, we're going to go over radicals, rational exponents, and rationalizing the denominator. See you then. Alright guys, we're going to go ahead and continue with section 1.2. And here we're going to go over radicals, some rational exponents, and such. So a radical, you guys have seen a square root sign. So the inside is called the radicand. And this whole thing is called a radical expression. So our b squared, it equals a. So our example is like square root 25. Because 5 squared equals 25, and then also negative 5 squared equals 25, we then know that this equals plus or minus 5. So it's not always true that the square root of a squared equals a. As we can see in this example, the square root of 4 squared is 16, which is 4, but also the square root of negative 4 squared is also 4. So this thing in the blue where it's square root a squared, it's going to equal the absolute value of a. So going on to the nth root. So the nth root is going to be the square root sign with the n. So typically when it's just a square root, the n is actually a 2, but we don't write it out. So this means that bn equals a. So some properties of n root. So it's the same thing as just with square roots, except we're going to carry the n. So example is 500. So we could break that up into 100 times 5, and then break those up even more, and then 10 is the square root of 100, and then we just keep 5 under. And there's another example there too, if you want to pause the video and look at it. So adding and subtracting radicals, they can be combined if they have the same radicand. So our square root 2 plus square root 8, we could break up 8 into 4 times 2. And then 1 times square root 2 plus the 2 here is from our square root 4. And so now they both have square root 2, so we can combine them. So we'll go ahead and add the 1 and the 2 to get 3 square root 2. And then we have rational exponents, which are fractional exponents. So we have a to the 1n is the square root of a with n equals b, which means bn equals a. So we have our fraction mn in lowest terms. So usually you write a to the mn with n, the denominator is going to be what your root is, and then m is the power that a, or the whole expression, is going to be raised to. So either one, whichever one you prefer, or whichever one works best for the problem is fine. So an example is the cube root of 64. It's 4 because 4 cubed is 64. So we could also write that as 64 to the 1/3. So here, our example 8 to the 2/3, it makes sense to write the 2 on the outside instead of the inside because we know the cube root of 8. That's 2. So we could do 2 squared equals 4. Another example is here when we have the product. So 5 times 7 is 35. And then we're going to be multiplying these two exponents. We're multiplying x to the 1/2 times x to the 3/4, and therefore we're adding the exponents. So we get x to the 5/4. So sometimes it's helpful to change roots to fractions in order to combine them, or it's just easier to see. So when we combine them, it's easier just to say, like, okay, I have 1/2, 1/3, like I'm going to add them instead of seeing them as square root symbols. So rationalizing the denominator, you've probably heard it's best not to keep a radical in the denominator. That's usually not true. It's usually okay to have the radical in the denominator, but just to clean it up and so you guys know how, I'm going to go ahead and go over it. So in order to eliminate the radical in the denominator, we're going to multiply by whatever's in the denominator inside the radical. So have it on the numerator and denominator, which is essentially 1. So here it's like 1 over square root a. We're going to multiply it by square root a over square root a. And that means that it's going to be square root a times square root a, which is like a to the 1/2 times a to the 1/2. So we add the exponent, so that's a to the 2 over 2, which is a to the 1st, which is just a. So here's another example. We're doing 1 over a squared, and then it's going to be the root to the 7th. So we're going to break up the fraction first. And so the root of 7 of 1 is just 1. And then we're going to change a to the 2 to 2/7 if we wanted to. So we're thinking, okay, what are we going to multiply it by in order to get the denominator to just equal a? So I'm going to go ahead and multiply it by a to the 5th with the 7th power, and I'll tell you why. So this here is a to the 7th, and this here is a to the 5/7. So when we multiply those, we're adding the exponents, right? So a 2/7 plus 5/7, that here is a to the 7 over 7, which is just a to the 1st. So that's the end of this video. We're going to go ahead and move on to section 1.3, which is algebraic expressions next. See you then.